Hey everybody. Today we're talking more about polynomials, focusing in on their zeros. Remember, a polynomial is just a function that has the form constant times x to a power, plus constant times x to a power, and so on, where all those powers are non-negative integers. So the exponents can't be negative and they can't be fractions. The highest power that you see is called the degree. Polynomials are your friend. The domain is always all real numbers. The graphs are always continuous and smooth. They don't have jumps and they don't have corners. A lot of times we factor polynomials, writing them as products of lower degree polynomials. For instance, negative 3x to the fifth plus 12x to the third has a common factor that we can pull out, negative 3x to the third. I pull that out and then in parentheses write the other two terms where I've divided each of them by that factor. So I'm left with x squared minus 4. That's a difference of squares. X minus 2 times x plus 2 is x squared minus 4. A root of a polynomial is a value that makes the polynomial equal to 0. So it's synonymous with a 0 of the polynomial. For instance, the polynomial from the previous slide, negative 3x to the fifth plus 12x to the third, has 3 roots. Negative 2 is a root because f of negative 2 is 0. 0 is a root because f of 0 is 0. And 2 is a root because f of 2 is 0. A couple of important facts to keep in mind when you're dealing with polynomials. First of all, every polynomial can be factored into a product of linear, that is first degree, and irreducible quadratic, that is second degree, terms. Now, actually doing that factoring may be very hard, but in theory, it can always be done. Secondly, a degree n polynomial has at most n real roots. There's a direct correspondence between roots, factors, and intercepts of a polynomial, y equals f of x. So suppose we have a real number, x equals a, and f of a is equal to 0. So we have a 0 of the polynomial. That's the same as saying that x equals a is a root of the polynomial. It's the same as saying that x minus a is a factor of the polynomial, and the same as saying that a comma 0 is an x-intercept on the graph of the polynomial. So whenever you have a root, you have a factor, and whenever you have a factor, you have an x-intercept. Each of those three things goes together. So factoring a polynomial is helpful in graphing, and vice versa. And each of those things are useful when you're solving the equation f of x equals 0. So going back to that first example, we have this factored version of the polynomial, negative 3x squared times x minus 2 times x plus 2. And we saw separately that this polynomial has roots x equals 0, negative 2, and positive 2. Now you can see those factors matching up with those roots. And if we graph the polynomial, we see each of those things matching up with the x-intercepts. Here we have intercepts at x equals negative 2, 0, and positive 2, just the roots of the polynomial. Now, as in that previous example, sometimes polynomials have repeated factors, things like x minus c to the k, where the root here is x equals c. We call k, the exponent on that factor, the multiplicity of the root. In that previous example, we had a factor of x squared, which we could view as x minus 0, quantity squared. So x equals 0 had multiplicity 2. So, for instance, the polynomial x squared times x minus 2 times x plus 5 squared times x squared plus 9 has 3 distinct roots. X equals 0 has multiplicity 2. That first factor we'll view as x minus 0, quantity squared. X equals 2 has multiplicity 1. X equals negative 5 has multiplicity 5. Now, there's that irreducible quadratic at the end, x squared plus 9. That does not give us any additional real roots. It cannot be factored into linear terms with real coefficients. Why do we care about multiplicity? Well, the multiplicity of a root gives us information about the function's behavior at the corresponding x-intercept. So suppose we have a polynomial f that has a factor x minus c to the k. so a root x equals c with multiplicity k. If that multiplicity is odd, then the graph is going to cross the x-axis at that root. For example, like y equals x does at x equals 0. I point that one out because y equals x is the simplest possible polynomial with odd degree, and its intercept is at x equals 0. If k is even, then the graph is going to touch the x-axis, but not cross. It's going to bounce off, much like the parabola y equals x squared does at its root x equals 0. For example, the function 0.01 x minus 2 squared times x plus 4 to the third has this graph. Let's look at each of the two roots. At x equals negative 4, we see the root has multiplicity 3, an odd number. So the graph is going to cross the x-axis there. Similarly, at x equals 2, we have a root with multiplicity 2. The graph is going to bounce off the x-axis there. It's going to touch the x-axis, but not cross it. Let's conclude by doing a more full example, sketching the graph of y equals negative x squared times x plus 2 times x minus 5 squared by hand. We have three roots here. X equals 0 has multiplicity 2, so the graph will touch the x-axis but not cross it. X equals negative 2 has multiplicity 1. The graph will cross the x-axis there. And x equals 5 has multiplicity 2. The graph will touch the x-axis there, but not cross. Let's also mention end behavior here. That'll be helpful as we graph this function. We have a fifth degree polynomial, and the leading coefficient is going to be negative. So here I'm imagining foiling this thing out and just asking myself, what am I going to get for the highest power terms? Well, just looking at the highest power terms, I'm going to be multiplying out negative x squared times x squared, basically ignoring the plus 2 and the minus 5. So I'd be getting negative x to the fifth. The end behavior of this function is going to be similar to that of negative x to the fifth. So on the left, the graph is going to go to positive infinity, and on the right, it's going to go to negative infinity. Y equals negative x to the fifth is going to behave in its end behavior just like the simplest possible polynomial with odd degree and a negative leading coefficient, y equals negative x. I'm going to start graphing just by labeling the information I have. I've put the roots on the graph at x equals negative 2, 0, and 5, and I've used arrows to indicate the end behavior. Also, I know that the graph is going to cross the x-axis at negative 2, and it's going to bounce off at x equals 0 and x equals 5. Can you picture this graph? Here's what it looks like. Again, crossing at negative 2, bouncing at 0 and 5, going to negative infinity on the right and positive infinity on the left. One very important warning here. This is only a rough sketch. It's giving us the general behavior of the function. Except at the x-intercepts, we have not really determined the value of this function at any point. So my sketch perhaps makes it look like f of negative 1 is negative 1. That's very likely to not be the case. We shouldn't attempt to calculate specific values for this function just by looking at the graph.